Today, we will learn how to deal with missing observations in data analysis. In many clinical research, it is almost impossible to avoid a missing observation. And when the missing observations become sufficiently large and is started by a single result. And many journals and journal reviewers are now aware of these problems. And so, last year, New England Journal of Medicine published a checklist and to provide guidelines to authors on how to deal with missing data. And in this guideline or checklist, they put the 5 items. And these are questions New England Journal of Medicine statistician might ask. Number 1, so they ask that the study has adequately considered ways to reduce missing in design. Okay? And did authors report the possible effect, consequences of missing if they propose analytical strategies to deal with such missing and in their study protocol? So, before you begin a study, you do have to take a time and think about how you can deal with those missing in data analysis. Okay, so here is the recommended ways to deal with missing observation. So if sufficiently large number of observations are missing, okay, and they might ask if you conducted sensitivity analysis and to assess magnitude of impact from ignoring such a missing in your data analysis. And sensitivity analysis, unfortunately there is no clear guideline, but the journals actually recommended some methodologies author might consider to use. Okay. And preferred method of analysis include weighted estimating equation and a multiple imputation. Okay, so in this lecture, and we are focusing on the multiple imputation, okay? And we will talk about the method. And so they ask if the author does not impute such a missing variable, okay, and just use complete data in analysis. Okay? They're asking you to justify complete case analysis. Okay, and or to use less preferred method of imputation. Okay? So today we will talk about which method they prefer and they don't prefer, and obviously, and they're liking to use multiple imputation. So this will be a focus of today's lecture, and we will learn how to do this in SPSS. And we don't really talk about weighted estimation equation in this lecture, but there is alternative method and you might consider to use, and you can do that in SPSS. That is called EM method. So today I will introduce you solo method and then with the focus of these 2 methods. So here is a motivating example for today. And we are going to use data from a support study. And support study is very famous study because data from support were used to develop Apache score, which is a prognosis score among patients in ICU. Okay. So we have 894 randomly selected data from a support study. Okay. And then we are going to predict hospital length of stay as an outcome variable. And so that's SLOS here as a function of age, mean blood pressure, heart rate, PAFI, and rest of these measurements. So you might think this analysis is very powerful because it includes 894 patients. And although you need to pay attention, is that really the number they used in their final regression analysis? And because SPSS or many statistical software automatically delete the entire row of observation, and if at least one of these variables are missing in the regression. Okay, so PAFI has 228 observation missing, bilirubin 265, and pH 225, albumin 330, glucose, BUN, and urine output, and then they have more than 400 observation missing. SPSS provide a nice diagnosis of missing values. And based on this, and you can say there are 9 total variables which has at least one observation missing. So you simply count these numbers, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? And then here, and SPSS can tell you how many observations, i.e. how many patient has at least one variable with missing data. Surprisingly, 720 patients out of 894 patients, one of the variables included in the linear regression being missed, and therefore final analysis only used the data from 174 patients. That's shocking news, isn't it? And then here, and you know there are a total of 11,861 observations and are missing. Okay, so which is more than 80% of entire observations. Okay, so this is, by the way, the prospective study. So when you have a retrospective study, and then you probably have more missing than this support study. So here is a result of a linear regression. And when, and you are not aware of this missing issue, and then just use SPSS to do linear regression. Okay. And by the way, I log transformed outcome variable. So outcome is log transformed hospital length of stay. And you put that in SPSS and plug all these independent variables in, and then run the regression. And you only include N of 174 patients. Okay? And then only mean blood pressure becomes significant. Okay. And then what I did is I went ahead to use a multiple imputation, which is the preferred method of analysis of missing data, and imputed such missing data, and then N become 894. Okay? And that's the numbers of patients, and actually was in this study. And effective mean BMI become more significant, and then 5 more variable actually show statistical significance. And temperature is really significant. Okay, but it was not significant in the original analysis because p-value is just above 0.05. So let's see what's happening in here. And obviously, and we did lose statistical power, right? Because we have only 20% of observation used in this analysis. So when you see the p-value, and this imputed analysis is a lot larger power because of the larger N. And the next, when you compare beta coefficient, if you start seeing clinically meaningful difference, and for example, effective bilirubin is now 1/3 of the analysis without imputation, and or effective temperature is actually greater with imputed data analysis than non-imputed data analysis. So change in beta is actually showing a bias. Okay? So when you don't deal with missing data in your analysis, and you can lose statistical power. Okay? And in this example, it was significant loss of statistical power. And then also, if the such a missing is not happening random, okay, and it will start biasing magnitude of association. We will talk about 2 types of missing. One is called random missing, and then the other is called non-random missing. And random missing, and we also call non-informative missing. And then non-random missing is informative missing. Okay. So we need to watch out more when the missing are not happening at random. Okay, so, and this can cause bias. And random missing, by the way, it can cause loss of statistical power. Non-random missing is both. Okay. Now, why the non-random missing is so important? Okay, so I'll give you an example. Non-random missing happen when the missingness is associating to both exposure variable and outcome variable. And for example, in RCT, and if the new treatment, with the new treatment, and patients are experiencing side effect, and because of that, and they start dropping out from your study. And when they drop out, obviously you can't really observe events. You will miss amount of events. The mortality would be lower, right? Be underestimated. And your result might indicate intervention actually works. But then it's just because of this missingness. And unfortunately, most of missingness happen non-random manner. Okay. And so let's learn how to deal with those. Before I introduce you to a method of imputation, and let's talk about what is random and what is non-random. And this slide indicates non-informative missing, where the missingness happen at random. Okay, so this example, y, let's delete. Y is a hospital length of stay, and then x could be okay. X is temperature, for example. Okay. This is a data without missing, so you observe everything. So every single patient you observe both temperature and hospital length of stay. And this shows a situation and you have random missing. So this orange dot are the data you did not observe. Okay, so in this case, even if you delete all these missing data, okay, you probably will draw this line very similar to when you didn't have such missing data. Okay, so when you have a random missing or non-informative missing, and it doesn't really bias association between temperature and hospital and length of stay. And although obviously, and you can still lose statistical power because you have less number of observation, but regression slope is unbiased. So when you have a random missing and complete case analysis, even with that, and if you're detecting statistical significance, it may be okay because with the loss of statistical power, you are already detecting the significance and beta coefficient is not biased. Whereas when you have informative missing, this is non-random missing. Okay, let's see what happened. Right? So this is a data without missing, and this is a data which contains some missing. Missing is happening more with a higher temperature. So higher the temperature, and you don't observe this temperature value. And let's see. Okay, so these are the data you observe. And if you draw a straight line on this graph, and you might draw the line here instead of here. Okay, do you see slopes are changing? Yeah, so this indicates the bias in association. Okay, so when you have informative missing, and regression slope can be biased, and also with less of observation, and you lose power. And so we do need to know what type of missing you have. And there are many methods developed to impute missing data. And the method used in most epidemiological and clinical studies to handle missing data actually are not perfect. So even with imputation with some of the method, it can still cause bias. Okay? And type in the severity of bias depends on the method you use to impute data, and then also type of missing data. So rest of today's lecture, and I will talk about what type of method are being used or should be used for what type of missing data. So let's start with the type of missing data. Okay. There are three types of missing data, and one we call it missing completely at random, MCAR, and second missing at random, MAR, and the last missing not at random, MNAR. And missing completely at random is actually ideal situation, and missing at random is something you may be able to do with statistical method. And when you have a missing not at random, and then that's worse, we can't really deal with the statistical method. Okay, so So severity of problems is 1, 2, 3. So you'd hope you have missing completely at random. So this is informative, non-informative missing. So therefore you might lose statistical power, but beta coefficient will be unbiased even when you ignore missing in the analysis. Okay? And both 2 and 3, and if you ignore such a missing and you start biasing your study result, not just the losing power. So let's start talking about each type of missing. Missing completely at random. And definition of MCRA is as follows. The probability that an observation is missing does not depend on anything except for chance. And so, for example, and you are carrying lab tubes and then you stepped on something and you dropped the tubes on the floor, and some tubes you lost and some tubes are okay. So such missing, okay, and it's totally at random, so it has nothing to do with patient characteristics or disease severity. Okay, so that's the situation for missing completely at random. SPSS can easily test such missing completely at random. I will show you how to do it later in another video. And there is a test called the little MCAR test, and if p-value is less than 0.05, and that indicate MCRA is not held. That indicate missing are not completely at random. Okay, but if this p-value is large, then that might indicate missing completely at random. In MCAR, and in many data sets, you may see small p-value here because in reality, a missing usually occur not at random. So here, SPSS provide nice graphical presentations, and if the missing are happening completely at random, and you see this red and scatter around this graph. So you shouldn't be seeing any patterns where the red or whites are. But here, this is telling, okay, and there are 47 different patterns, okay, and most common patterns is 31, and where and BUN and glucose and urines are missing. So there are about 27% of observation, 450, okay, so 400 patients, and they are missing all 3 variables. Okay. So this means, in the previous slide, person who missed glucose and also missed BUN and also missed urine output, okay, and also pattern 47, and all 9 variables are missing. And so here there is no frequency here for 47th, but percent of people who doesn't have any of these 9 variable are less than about 3% maybe. And so so by looking at this, and then the second largest pattern is number 1. So number 1 is not missing, so that's n equals 174 patients following this pattern. Okay, and then third largest pattern is number 11. So that's where bilirubin and albumins are both missing. So when the missing are happening completely at random, and you shouldn't be seeing any patterns here. So you have random white and red, but here you clearly have a pattern. So that's indicate not completely at random, so that reflect on small p-value here. And here is another method to assess if the missing is happening at random or not. So what I did is I created the new variable called ever miss binary, ever miss b. So this will be 1 for patients who have at least 1 observation missing, okay, and then 0 for complete data without missing. Okay. And so there are 174 complete cases and 720 patients have at least 1 variable missing. And then we compare outcome variable and then also each of independent variable. And so you can see person who have at least one missing tend to have a shorter hostel length of stay than a person without missing. So this is the median value, and this is the interquartile range, and this is the mean value plus minus standard deviation. And age in person with missing, and mean age is 63, median is 65. And person without missing, mean age is 60 and median age is 62. So younger the patient, and they have more complete data. Okay. So you can eyeball, and then if the missing happening completely at random, and you expect not many p-values are statistically significant. So this is a quick this type of table, and we put in a paper and show even with the missing and missing happening at random, therefore we can proceed with complete case analysis. Although now after you learn how to do imputation, probably it's better to impute data anyway. Okay. So next two types, missing at random and missing not at random. And missing at random is different from missing completely at random. Okay. In missing at random, probability of missing an observation depends only on the other observed value. Okay. So let's see, in this regression, and you have these many independent variables. So if you can explain who is missing on BUN and with other observed variable, and then you have missing at random. For example, in a study of asking risk of lung cancer, smokers tend to have missing on smoking variable. Who smokes can be predicted completely by knowing age, gender, income, and alcohol drinking status, and all of 4 variables are observed. Okay, and whereas missing not at random happen when the probability that an observation is missing depends on unobserved values. So in this case, okay, in the same example, and missing, are completely explained by knowing age, gender, income, and alcohol drinking status. And although in the data collection you only collected age and gender, but you do not know alcohol drinking status and income. So then we can say this type of missing is missing not at random. Another example of missing not at random is, for example, probability of missing on variable depends on the true value of that variable. For example, a marker value below threshold. So if the marker value is less than a threshold, and we don't observe, the missingness is completely depending on the missing variable, missing value itself. And you might think you could predict those missing whose value is under detection limit knowing other markers, although other markers also have detection limit. So in that situation, it's really hard to impute because person who have missing value also miss other variables. And when missing happen not at random, unfortunately there is no general method for dealing with such missing. And then many medical data or clinical data have missing not at random, and then it's not possible to test whether missing is missing at random or missing not at random because we do not really have unobserved data, right? So this is a catch-22. So as you see, when you have informative missing, could be MAR or it could be missing not at random, okay? And you lose statistical power, and also you bias regression slope, you bias association. So here we do need to know special techniques to deal with it, and but none of them really works with this. So we are trying to deal with at least missing at random data. So let's review the mean imputation. The mean imputation, you replace missing of a variable. Let's say you have a BUN contain missing, and then missing BUN, and then you replace with mean of BUN from other patients. So we use this value to compute mean, and then replace with this. Okay, and then this person has missing BUN, so I'll replace with 32. Okay. And as you might have noticed, in persons who miss BUN and their imputed values are all the same. So this method is criticized it cannot bring randomness in imputed data, therefore p-value tend to be too small, and then also this biased the true association as you saw in this demonstration. So this doesn't work even with missing completely a random data. And as you see in this case, and usually effect is biased toward the null value. Okay? So here's how you do mean imputation in SPSS. So first in U, here is how you do mean imputation in SPSS. And first you create a new variable by copying BUN, okay? And then give some meaning. Okay? And then use a condition. So if the missing BUN equal 1, so this means there is a missing in BUN, and then replace with mean of BUN. Okay, so you can easily do imputation using SPSS, although this is not recommended. And there is a method called indicator method. An indicator method, and you need to create a two variable. Right? So this indicator variable, and then you return 1 for missing BUN, 0 for non-missing BUN. And then also you create BUN imputed variable, and by replacing missing with 0, okay, and then retain non-missing value for non-missing observation. And in the regression analysis, instead of including BUN, okay, you include BUN imp and indicator. Okay, so this way all values are not missing, so you can retain entire observation. And this had been used a lot in old days, but we now know this method is a biased method even when you have missing completely at random. It doesn't work, and it doesn't work, of course, MAR. And Dr. Moons had published a paper in Journal of Clinical Epidemiology and showing and how the missing indicator method does not work. So if you want to learn more, and please refer to this paper. Okay. Regression method. And the regression method, you perform regression. So if you want to predict missing BUN, okay, you perform regression where BUN is outcome and as a function of other variable. Okay. So and then using a formula, so you know you will have beta coefficients and intercept for this regression, and use that formula, and then to plug, for example, if you want to impute this missing BUN and you plug in this value to this regression, and your predicted value for BUN you replace with this BUN, and then you do the same for albumin. Okay, so if you want to impute missing albumin level, do the regression where albumin is outcome variable. Okay. And then after you get the formula and you plug in these values, no missing value for that person you want to impute missing for albumin. And the problem with this approach is, as you see, okay, and if this person, let's say compare these two persons, okay, these two persons, and then these two persons actually share exactly the same value for non-missing variables, and then this value will be replaced with 3. Okay. And so again, similar to mean imputation, and this method does not consider randomness, therefore p-value tend to be too small. Okay, so therefore don't use. This method is better than mean imputation because amount of bias is less, and although p-value becomes too small. Okay, so don't use. Another method for imputation is called EM method. And this method utilizes mathematical technique called expectation maximization. And this is similar to regression method where it utilizes other variable to impute missing value. But advantage of EM method over regression method is this iteration process. And so they use the value of no missing variable to impute missing, and then it compute maximum likelihood and then see how likely the missing value is. And then if it is not maximum value, and then it's repeat iterations and re-impute based on the observed value, and then checks maximization, and then it stops when it reached most likely value. So this iteration process and this EM imputation is better than regression method. And New England Journal of Medicine recommendation mentioned weighted estimating equation, and the EM imputations are thought as good as weighted estimating equation. And so let me give you a peek of a method of dealing with missing data. And in the case, missing is happening not completely at random. This data set does not have any missing. So you observe everything. So you know true association between X and Y here. Right? And when the data contain missing, okay, so that's here, and you don't observe these data. So if you ignore missing and just use complete cases, and then your association you detect from the analysis can be biased. You see this slope is slightly different from this slope, right? There is a method called the mean imputation. And mean imputation, you replace in these missing value, because you don't know what these value, with the mean variable of observed data. So you compute mean of these observed y, and then replace this missing with mean. Okay, so mean this is where you expect means are. Okay, so all missing data you replace with mean of y. So you are creating this cluster of imputed data around mean of y. So when you do that, let's see what happens. Okay, you plot regression line on this, and this regression line is also different from true association. Okay, so mean imputation being used a lot, but it's not the recommended method. And this doesn't work even with missing completely at random data. And single imputation is a technique. And number 4, there is a method, and you can use information from other variable, not just y and x, to impute missing data. And for example, and you are missing a lab value. Say you know hospital length of stay, but you don't know the marker value. Okay, so the marker could be C-reactive protein. So you are not observing CRP, but you may observe IL-18. Okay, the other marker value. Right, so these are IL-18 or IL-6. Let's change it to IL-6. Okay. Right, and then what you do is using this green information, green dot, and you impute this salmon pink dot. Those are missing data. In order to impute this person's missing data, you borrow data from this screen. So this is IL-6 of this person who has missing CRP, okay? And then impute this value. In order to impute this person's CRP, you borrow this person's IL-6 value and then impute. And so that would be somewhere like here. And in order to impute this value, and you borrow data from this person's IL-6 and impute this value. So that would be close to here. Okay? Because you have the same Y but a different X here. And then do that for other missing CRP. Okay? So this is a method. There are several methods to do this. A regression method and an EM method, in which I will explain later. And all the methods so far I've introduced is a single imputation. The word single imply how many data set we are computing out after imputation. So single imputation only create single set of imputed data set, which include method of mean imputation, regression imputation, indication method, and EM imputation, and our last observation carried forward method. And this should be C. And the downside of single imputation is its statistical power resulting in too small p-values. So it is better to use a method and solution to this problem is to use a multiple imputation. And a multiple imputation and create multiple data sets based on imputation. And so instead of creating just a single data set, and we create, let's say, sample size and equal 894, okay, and 5 sets of data set, each contain and equal 894, okay, and this imputation process involves randomness. So each imputed data sets are slightly different, and more observation being missed, variation among these imputed data sets become larger. Okay, and then what happens next is using each imputed data, and you perform linear regression of your interest. So in this case, we use hostile length of stay as outcome variable, and then we put independent variable, which is age, or temperature, or albumin, and so on. Okay, all those variables you saw in beginning of this lecture. Okay, so for each observation, each imputed data set, and you do a linear regression. Okay, and let's say you are interested in assessing effect of albumin on hospital length of stay. So first data set, compute beta 1 as effect of albumin, and second data set, compute beta 2, and third data set, compute beta 3, and fourth data set, compute beta 4, and fifth data set, compute beta 5. And these are beta coefficient for albumin based on these linear regressions. And then at the final stage, and you pull these beta coefficients, okay, and then pull the beta coefficient, you present as a final beta coefficient for this imputed data set. And as you see, the more missing you have, there are more variation among these data set, and that variation reflects on the variation in these beta coefficient. And therefore, when the percent of missing is large, and this reflects bigger variation of these beta coefficient. Okay, and these are all for albumin. And therefore, amount of missingness actually is considered in calculation process. So therefore, using multiple imputation, and we do not need to worry about inflation of sample size, and so p-value is not too small. Let's review multiple imputation. And multiple imputation, and in a sense, they borrow information from other observed variable to impute missingness. It's similar to EM method or regression method. But the difference is multiple imputation, you impute multiple data set, and in each data set, and you fit a regression of interest. And then finally, you pull these beta coefficient, and then present the pulled beta coefficient as a final result. Okay? Alright. Here is a summary of comparing imputation method for each type of missing data. And when you have missing completely at random, okay, in complete case analysis, you ignore missingness and you lose power, but beta coefficient is unbiased. But when you use mean imputation indicator method, and beta coefficient will be biased. And when you have missing at random, complete case analysis will bias the result. And mean imputation indicator method does not work for any type of missingness. Okay? And regression method and provide unbiased estimate for regression method and EM method, and provide unbiased estimate for both MCAR and MAR, and although it's inflate statistical power, okay, p-value become too small. And same for missing at random, MAR. Okay, and the multiple imputation is good because it does not inflate statistical power. Okay, and then beta coefficients are unbiased. When you have a missing not at random, neither method works, okay, because we don't really know what the variables are associating to missingness. So none of the statistical method really works with missing not at random. And many research data sets are missing not at random, but that doesn't mean you shouldn't even do anything. And the method you use for missing at random, even if it's not perfect, but it does provide a more unbiased result compared to ignoring those missingness. Okay, so let's read one more time New England Journal of Medicine checklist. That the study has adequately considered ways to reduce missing in design of the trial. Did authors report the possible effect, consequences of missing, and thought analytical strategies to deal with those missing, and then report it in the study protocol? Okay, number 1 and number 2, okay, please do. And number 3, is there adequate justification to use complete case analysis or single imputation? So when you use a method which is inferior to the available method, like multiple imputation or EM method, and you need to justify use of such a method. So when you totally ignore and analyze data only with complete case analysis, and you need to prove you have missing completely at random, and such includes computing p-value based on little method for MCAR, or compare baseline characteristics between incomplete data versus incomplete data set. Okay, and when the sufficient number of observations are missing, it is always better to include sensitivity analysis using some imputation, and such as MI method or multiple imputation. In the journal preferred MI or EM method, and then I think, my personal opinion, it is okay to use imputed analysis as your main analysis. Okay? And the important thing is decide which one you present as a main analysis, and then write it down in your study protocol before you begin the study. Okay. I think more and more studies start using imputed method as a primary analysis of a choice. So now let me talk about missing in the longitudinal study. And many of you have heard last observation carried forward method, LOCF. And this is a method, and when you conduct a longitudinal study, and like prospective cohort study or RCT, and that patients are supposed to come back multiple times during a study, and then you make assessment when they come back. And some people probably come back at 6 months and then never come back after that. And this study is thought to follow everybody to 12 months, and then ID 2% never come back after 6 months, and ID 3% never come back after baseline was measured. And last observation carried forward method, okay? And you use whatever the measurement made most recent to replace with end of the study value. And then, so the ID number 3%, baseline is the only measurement, so you carry with baseline, you carry baseline value, okay? And then analysis use end of study value as an outcome variable. And this LOCF was heavily used in the past, but recently being criticized. So it's better not to use this method. And why is that? Let me explain. Okay, so when assuming you're conducting RCT and patients are supposed to come back every month for 6 times. Okay, so baseline, visit 1, visit 2, visit 3, visit 4, visit 5. Okay, and this scenario is showing control patient stop coming back, and so you carried forward the last observation and then use that value as outcome of the analysis. Okay, and then difference between treatment and control would be this much. Although if this patient come back to the study end, and actual result would be this small. Okay, in other situation, and suppose person who stopped coming back is in the treatment arm. Okay, and then if this person come back to the end to the study, and then you would see slight improvement by the treatment, and although this person stopped coming, and then at the result, and then you carried forward this value. Okay, and then now you are seeing harm by treatment and assuming lower value reflect a better outcome. Okay. So therefore, the last observation carried forward method, the results are not really robust, and result of analysis are influenced by the pattern of missing, whether you have a more missing patient in control group or more in treatment group. Okay, and instead, a better analytical method is to use repeated measures analysis, such as a mixed effect model. So here is a reference, and if you want to learn more. And by the way, mixed effect model and GEE are both the model for repeated measures analysis. And the mixed effect model actually is better, more robust for missing data because it's assumed missing at random. And GEE assume missing completely at random. Okay. So when you're using GEE, it may be better to impute missing data before you conduct GEE. And we will talk more when we learn repeated measures analysis. Okay. And there are several great papers published by Dr. Moons. And this paper talks about dealing with missing outcome data in randomized trial. And what they found is it's actually better to impute outcome data as well. And they compare a method of ignoring the reference means there is no missing. All the observations are observed. And analysis totally ignore missing. So that's complete case analysis. And analysis use single imputation. Conditional mean imputation is impute with mean or impute with the regression method. And a multiple imputation method, and we talked about this method, right? And then they created the scenario where the data are missing at random or missing not at random. And as you see, when the data are missing at random and then using method to impute outcomes, okay? And you have, so 0 means non-biased result. And imputation works pretty good. when you have non-random, when you have missing not at random, okay? And when you impute outcomes and you don't quite fix the problem with multiple imputation, although the result you obtain from multiple imputation is much better than the analysis ignoring such a missing. And here is another reference, Gentle Introduction to Imputation Missing Values. This is easy to read paper, and it doesn't have much math equations. So I highly recommend you to and this is another paper, and to talk about dealing with missing as a predictor variable when applying in the prognosis prediction models. And then they found even when you have a large amount of missing, such as 95% data are missing, it is better to use multiple imputation to impute missing rather than ignoring those missing.